Okay, so we are going to talk about Category 2, graphing systems of linear equations and inequalities. So it should be the middle of your flipbook. So first we got to talk about what a system of linear equations is, and it's simply two or more linear equations. Now in Algebra 1, you are specifically working with two equations at the same time. Okay, and the solution or the answer to a system of equation is the common ordered pair. So you need a common x and a common y value, and this is where the equations intersect. So if we are looking at the picture of our system, we should see two lines. So you can see here we have two equations. Here are their y equals equations, and here are the graphs of those two linear equations. And you can see that they intersect at this common point right here. Well, I just need to figure out what is the x and the y value for that ordered pair so that I can get the solution point. Because yes, they have one common point. Yes, one. And that is important. Okay, so I want to be able to tell what the ordered pair is for that. And if I look at the x value, that is -3. And if I look at the y value, it is 1. So remember, a solution really contains two answers. You've got an answer for x and an answer for y that you write as an ordered pair. Sometimes they just ask you for one. Okay, so what happens if you're looking at a graph and you don't have lines that intersect, meaning you have parallel lines? Do they have a common point? No. And the reason why is because they're never going to cross, they're never going to intersect like the first graph did. And so your solution would be no solution. There is no ordered pair. And notice I'm not writing 0 because 0 could be confused with an x or a y value, so I want to make sure I'm very clear that there is no solution. That means they never cross. Now one thing I want to draw your attention to is when you solve both of these for y equals, if you look at the slope of parallel lines, remember that your slope value is always the same. So that's how you're going to know they're parallel if you just have the equations. Make them both y equals and look at the slope. So next you want to look at the third scenario that you could run into or situation, and that is where you only see one graph line. Now what you want to do is you want to make sure that both of your equations are in y equals format. So I'm going to rearrange the second equation and I'm going to move that x over. So I'm going to have y equals -1 minus x, and then I want to look at their slopes. So if you notice, both slopes are the same. It's both -1. And then you also want to look at your y-intercept. And if you look at your y-intercept for both equations, you notice that your b values are also the same. So this is a trend or a pattern that you see with slopes and y-intercepts to know that you are dealing with one graph line. This is two lines that are the same. Two lines that have the same slope and y-intercept. Okay? Same slope, same y-intercept. So do they have any points in common? Yes, they do. Every point is a common point. So if I don't want to list all those ordered pairs out that make that equation line, so what I'm going to do is to make it easy, I'm just going to say there are infinite solutions. That list of ordered pairs is way too long for me to list out all the x and y values. Okay, so I'm just going to shorten that up and say infinite solutions. Okay, so let's talk about graphing a system of linear inequalities. So remember, a system of linear inequalities is just when you have two inequalities. So what we're going to do is we're going to talk about now the solution. The solution to a system of linear inequalities is the set, and that should tell you that there's more than one. If you have a set of points, you have more than one point. So the solution is the set of every ordered pair. So it's all your points that fall in the double shaded region. And it's important to note that they have to be where the shading overlaps, okay? Because remember, inequalities, you have shading. And since you have two inequalities, you're going to have two shadings. And you want to look at where it overlaps. So let's look at graphing this. So I've got y is less than or equal to 3x plus 4. So let's take a look at that. So my slope is 3. And that's going to tell me up 3, right 1. Because if I make this a fraction, it's really going to be 3 over 1. But I need to know where I'm starting at. And I'm starting at a y-intercept of 4. So I'm going to go to the y-axis at 4. I'm going to make a point. And now I'm going to go up 3, right 1. Up 3, right 1. I'm off the graph. And now I'm going to go back here and I'm going to go down 3, left 1, down 3, left 1, down 3, left 1. Now, I need to look and see if I need to connect, and I see a solid line on my symbol. So yes, I need to connect this graph line, and I'm going to put arrows to show we would keep graphing it if we had it. And now we need to shade. So I'm going to get my pink highlighter. And now we're going to shade. So I need to look at my inequality line. Since it's a less than, I'm going to shade under the line. So I'm going to shade down from the line, and there's that graph. And now I need to graph the other inequality. And so it is y is less than negative 2x minus 1. And so now I'm going to look at my slope. My slope is a negative 2, which would be a negative 2 over 1. So that's telling me down 2, right 1. And it's going down 2 because it's negative. But I need to know my starting point. My starting point's at the y-intercept, which is negative 1. So now I'm going to go to negative 1. And I'm going to go down 2, right 1. Down 2, right 1. And now I'm out of graph's coordinate plane, so I'm going to go back to my initial value, my y-intercept, and I'm going to go up 2, left 1, up 2, left 1, up 2, left 1. Now, this symbol has no solid bar on it, so I am not going to connect. I'm going to make a broken line. So I'm just going to make little pieces of a line over those ordered pairs, and I'm going to put an arrow to show that we would keep going if we have more coordinate plane. And now I have to shade. And because it's a less than, it means I'm going to start at my line and I'm going to shade down from my line so that I get on the less than side. So I'm going to shade down like this. And now I'm looking at that double shaded region. So I'm looking where my two shadings overlap, and they overlap right here in this triangle area. Now remember, that triangle area is going to grow because these lines are going to keep going. So everything that falls in this little triangle area, if I extend these lines, all of these ordered pairs that fall on those in that shaded area is going to be a solution. Now, any point on the solid line from here down is also going to be part of the solution, because remember, being on a solid line counts as part of the shaded area. So now what we're going to do is we are going to graph and see if these ordered pairs fall in the double shaded region. So I'm going to now plot I'm going to try to use a pink one to see if it shows up, negative 1, 0. And that falls in the double shaded region, so yes, it is a solution. And then I'm going to do negative 1, 5. And you can see very clearly that that does not fall in the double shaded region, so no, it is not a solution. And then prove algebraically. So if you have an ordered pair, a test point, you want to plug it into both inequalities to prove that it is true. So we're going to take inequality number 1. And wherever I have a variable, I'm going to put an empty parentheses because I want to plug in the x value and the y value for my test point. So I'm going to plug in my x value here where x goes, and that value is 0. And then I'm going to plug in my y value where the y was here, and I'm going to plug in negative 3. And now I'm going to do the math. So I'm going to end up with negative 3, because there's no math to do before the inequality, is less than or equal to, and now I'm going to use my calculator, and I'm going to say 3 times 0, and then I'm going to add 4 is 4. Okay, so now I'm going to ask, is this true or false? Is negative 3 less than or equal to 4? And that is true. So the test point works for the first inequality, but now I have to check it for the second inequality. So now I'm going to do y is less than negative 2x minus 1. And so I'm going to plug in for my x value right here in this empty parentheses, and I'm going to plug in 0. And now I'm going to plug in for my y value here, and I'm going to plug in negative 3, and I'm going to do the math. All right, so is negative 3 less than, and now I'm going to do the math on that side, I'm going to get negative 2 times 0, and then I'm going to subtract 1. So you can see my calculator, and that is negative 1. Okay, is negative 3 less than -1. And that answer is also true. Because the further left you go on the number line, the smaller your numbers are actually getting, even though that 3 is bigger than 1. But when we're talking about negatives, the further right you go, the smaller it is. So it is true. So yes, this is a solution. And you can also see if I plotted 0, -3, it does fall in the double shaded region. So that is how I prove it algebraically if I don't have a graph to shade or to draw. All right, so let's talk about no solution. So let's look at this graph. So you can see here I've got y is greater than or equal to 2x plus 3, and that's got to be the solid line. And if it's greater than, that means I would shade up from the line. So I'm going to go up from this solid line. Okay, and now I have y is less than 2x minus 2, and that's the broken line because there's no bar. So it says less than, so I'm going to shade down from this line. And this is why it is no solution, because there is no double shaded region. Okay? None of the shadings overlap, so therefore there's not going to be any ordered pairs in that double shaded region, and that's why it is no solution. So don't assume because it's parallel lines, you have to look at the shading when you're talking about systems of inequalities.